Welcome to week 3 of the course. In this video, I'm going to review Stewart's entire acid-base model in just a few minutes. In week 1, we briefly discussed some of the key problems of the conventional approach to understanding acid-base balance. We looked at the problem of dependent and independent variables and asked ourselves what it is that actually changes hydrogen ion and other weak ion concentrations. For example, is the effect of adding hydrochloric acid or sodium hydroxide due to the addition of hydrogen ions or hydroxyl ions respectively, or could it be something else? As you will recall, we eventually concluded that it's the strong chloride and strong sodium ions that made the difference. We said the same thing about bicarbonate ion. We specifically mentioned bicarbonate ion because it is so frequently used in acid-base analysis, and the effect of administration of sodium bicarbonate is often said to be due to the bicarbonate ion. However, we soon saw that it is the strong sodium ion that does the trick. We also discussed the fact that the Henderson-Hasselbalch equation is correct but insufficient. It works well if we want to calculate pH, and we have the bicarbonate ion and carbon dioxide concentrations, or we could calculate the bicarbonate ion concentration if we have the pH and carbon dioxide. But it's completely insufficient to fully understand acid-base. In fact, it is just the logarithmic form of but one of a number of conditions that must be satisfied simultaneously in the analysis of acid-base status. In week 2, we began with pure water and examined the effect of temperature on the determination of hydrogen and hydroxyl ion concentrations. We saw that in the case of pure water it was always acid-base neutral, but that the actual concentrations of hydrogen ion and, of course, of hydroxyl ion is entirely due to the effect of temperature. Importantly, we saw that for pure water, the entire analysis depends on the existence of two equations which describe conditions which must be satisfied simultaneously. We then moved on to the definition of strong ions, which are defined as ions which are only found in fully dissociated form in solution. And the concept of strong ion difference was then explained. We examined the effect of adding strong ions to a solution and noted that there are still only two equations that determine acid-base status, but that this time the nature of the strong ions, that is cations or anions, change the ratio of hydrogen to hydroxyl ions and together with temperature determine the hydrogen ion concentration. We soon recognized that strong ions are key role players in acid-base. The addition of a weak acid was the next step. This extended the analysis to 4 equations, and we were able to see how the curves shifted so that a neutrality point was achieved at a more positive SID value than in the case of pure water and strong ions alone. We also briefly wondered about the effect of adding a weak base. We mentioned the fact that weak acids were primarily proteins, and that we've made a number of simplifying assumptions, including the lumping together of all weak acids into a single notional weak acid with a representative dissociation constant. Finally, we added the last constituent to complete our analysis of plasma. This was carbon dioxide. We stated that this produced the complete Stewart model of 6 simultaneous conditions, and we showed the solutions graphically. We examined the effect of changing the partial pressure of carbon dioxide by sweeping it through a range of values from very low, for example in hyperventilation, to very high, for example respiratory failure. We noted that the hydrogen ion concentration always increased with increasing carbon dioxide. However, if we fixed the weak acid concentration, the hydrogen ion concentration would decrease with increasing SID values for any given carbon dioxide level. If we regard sodium, potassium and chloride as the only strong ions, then SID would be roughly 40 millimoles per liter under normal physiological conditions. And then the normal hydrogen ion concentration would occur at a partial pressure of carbon dioxide of about 40 millimeters of mercury in arterial blood, as you can see on this curve. If we now fix the SID and change total proteins or weak acids, we see that the normal hydrogen ion concentration occurs at about here. Finally, we get to bicarbonate ion. We see that it does increase with increasing respiratory failure, in other words as CO2 increases, but this effect is rather small. Such non-respiratory, or as they were called metabolic effects, as changing SID, have a big impact on bicarbonate ion concentration, and thus we use bicarbonate as an indicator of non-respiratory changes to acid-base status.